Welcome to EPG Pathshala. Today we are going to discuss on biodiesel production from lipid sources. Biodiesel is the monoalkyl ester of long chain fatty acid produced from the lipid source, that is either vegetable oil or animal fat, and main process behind this is transesterification process. Government of India launched National Mission on Biodiesel in 2003 with a mandate of 5% blending with diesel. They thought that will reduce the emissions from the fossil fuel burning. Biodiesel has the good or the advantages over the diesel because of its no sulfur content and oxygen content of around 11%. The biodiesel production over the world depend on vegetable oils, but developing countries like India, we can't rely on the edible oils. So, mainly we are focusing on the non-edible oil seed crops, that is tree-borne oil seeds. When we talk about biodiesel, the name of the crop comes is Jatropha curcus. It is an introduced species. Under this national mission, the subsidies are given for planting the Jatropha over the field. But later on it was found that this crop cannot be grown without any inputs and it is some sort of failure. So, nowadays the R&D is more focusing on the non-edible crops which is indigenous to our country like Pongamia, Mahua, etc. In this module, we will be dealing with biodiesel, what is esterification, how the biodiesel is produced from transesterification process, what are the different types of transesterification, what are the feedstocks used in biodiesel production, what are the factors affecting the biodiesel production by the transesterification process. We will also see the advantages and the demerits of biodiesel utilization. The word biodiesel refers to a fuel made from biologically derived resource that has similar properties of those of petroleum based diesel. As per ASTM, the American Society for Testing and Materials defines biodiesel fuel as monoalkyl esters of long chain fatty acid derived from a renewable lipid feedstock, that is vegetable oil or animal fat, which is more suitable substitute to the diesel fuel. Biodiesel was first used in 1900 when Rudolf Diesel reported or he demonstrated that diesel engines can work with peanut oil. This biodiesel can be used directly in the engine or can be blended with the diesel. Normally, up to 20% blending, there is no need of change in the engine type, but afterwards there is a modification required. A blend of 20% biodiesel with 80% diesel volume is termed as B20, capital B20. The 20 stands for the percentage or the proportion of biodiesel added to the diesel, and this is the most common blend in most of the countries. A blend of 5% biodiesel with 95% diesel is designated as B5 and 100% is designated as B100. What are the feedstocks used for the biodiesel production? The main one is the edible oil seed crop. The oil content in various edible oil seeds like canola, cottonseed, peanut, soybean, sunflower, coconut, olive, palm oil is shown in the table, and it ranges mostly from 30 to 50%. The biodiesel derived from the different sources of this vegetable oil is a debate between the food versus fuel. The another feedstock is non-edible oil seed crop, commonly known as the TBOs, that is tree-borne oil seeds crop. The different non-edible tree-borne oil seeds are identified, and the major one over the world is the Jatropha curcus, which is commonly known as Rathanjot. It is a drought resistant perennial shrub which is growing in the different types of soil, and it belongs to the family Euphorbiaceae, and it has an oil content in the range of 37 to 40%. The other promising non-edible sources, especially to Indian context, are neem, which is Melia azadiracta, sal, mahua, kusum, soapnut, kokum, chirua and tung. The biodiesel can also be produced from waste cooking oil, that is the oil which is used after cooking, mainly which is left over after the chips production and other usage, other frying activities. So, it is also designated as WCO, which is waste cooking oil, or WFO, which is waste frying oil. Biodiesel production can also depend on microalgae. Synidesmus dimorphus, Chlamydomonas, Reinhardi, Chlorella vulgaris. They have a lipid content of around 15 to 40%. All over the world, edible oils are widely used. Germany and France are the leaders in biodiesel production. The primary feedstock for biodiesel production in United States is soybean. In Europe, it is rapeseed. In Southeast Asia, it is palm. Indian Railways was successful in its trial run by using 5% biodiesel as fuel in Delhi Amritsar Shatabdi Express in 2002. The Government of India's Planning Commission set a target of 11.2 to 13.4 million hectares of wasteland to be planted with jatropha in order to produce sufficient biodiesel to blend at 20% with this petroleum based diesel. Let us see what are the properties of biodiesel. The chemical composition of fat and oil esters is dependent upon the length and degree of unsaturation of the fatty acid alkyl chains. Biodiesel has hydrocarbon chains, generally 12 to 20 carbons in length, and contain oxygen at one end. It is known as oxygenate. It contains 10 to 12%, approx on an average it is 11% oxygen, which lowers the energy density and hence lowers the particulate emission. It has a specific gravity in the range of 0.86 to 0.9 gram per cubic centimeter. The cetane number of the biodiesel is 48 to 55, while the petroleum diesel has cetane value of 46 to 47. It is a desirable property in the diesel engine fuel efficiency. The flash point of neat biodiesel is always higher than that of petroleum diesel fuels. So, it is a safer fuel than the petroleum based diesel. This table shows the properties of biodiesel and diesel. This biodiesel is produced from jatropha. So, you can compare the jatropha oil, jatropha biodiesel and diesel with different properties of fuel like density, viscosity, flash point, pour point, water content, ash content, carbon residue, acid value and calorific value. You can see that the calorific value is little bit lesser than diesel. It is around 39 megajoule per kilogram. Coming to transesterification process, it is also known as alkolysis. Is the reaction of an oil or fat with an alcohol to form ester and glycerol. Here, the triglyceride present in the oil or fat reacts with the alcohol in presence of a catalyst, produces fatty acid methyl ester, fatty acid monoalkyl ester along with the byproduct glycerol, where in this equation you can see that the R1, R2, R3 represent different fatty acid chains, and the R, OH, which is the alcohol, this R is varying with respect to methanol, ethanol, etc. And finally, the monoalkyl esters you can see with R1, R2, R3 as per the substrate used for the biodiesel production. You can see the stoichiometric material balance which yields fat or oil with 3 molecules of methanol. That means, 1 molecule of oil or fat requires 3 molecules of methanol, which gives 3 methyl esters along with glycerol. You can equate or the stoichiometric balance, you can see the balance in this slide. Alcohols that are used in this transesterification process are methanol, ethanol, propanol, butanol and amyl alcohol. Among all these, methanol and ethanol are used frequently, and especially the methanol because of its low cost, polar nature and shortest chain length. It can quickly react with triglycerides and sodium hydroxide easily dissolves in it. So, mostly methanol is used in the transesterification process. This reaction can be catalyzed by alkali, acids or enzymes. The alkalis include sodium hydroxide, potassium hydroxide, some carbonates of sodium or potassium alkoxides. The acid catalyzed include sulfuric acid, sulfonic acids, hydrochloric acids, etc. And the biocatalyzed are normally the lipases. What are the different types of transesterification? This is mainly based on the catalyst used in this process. It is divided into two categories: homogeneous catalyzed transesterification and heterogeneous catalyzed transesterification. The homogeneous catalyzed transesterification is further divided into base-catalyzed transesterification and acid-catalyzed transesterification. Base-catalyzed transesterification. This is conventionally used in the industry using base-catalyzed, as we have already seen, sodium methoxide, that is alkaline metal alkoxides or hydroxides. Alkaline catalysts are less corrosive than acidic compounds and give faster reaction rate than acid-catalyzed reaction. It is this alkaline metal alkoxides are more active catalyzed. They give greater yield in short reaction time, but their requirement of absence of water makes them inappropriate for industrial use. So, normally hydroxides gain the importance. The most important advantage or the most important part of this process is its low temperature and low pressure conditions. So, it can be conducted in the normal room temperature, but they are limited by the free fatty acid content of the feedstock, which on reacting with alkali forms soap and reduces the yield of production. Normally, the preferred FFA content for this process is in the range of 0.5 to 2%. This is the mechanism involved in this base-catalyzed transesterification. It involves 4 steps: reaction of base with alcohol to form alkoxide with protonated catalyst. Further, nucleophilic attack at carbonyl carbon of triglyceride molecule by alkoxide ion to form tetrahedral intermediate. Further, the third step, rearrangement of the intermediate to give rise to alkyl ester and a diglyceride anion. Diglyceride anion deprotonates the catalyst, forming active catalyst and diglyceride. So, the diglyceride and monoglycerides are transformed into alkyl esters and glycerol using this mechanism. So, from one molecule of oil or fat, 3 molecules of monoalkyl esters of fatty acid are formed. Acid-catalyzed transesterification. This process uses the acids like HCl, H2SO4, sulfonic acids and phosphoric acids. It is insensitive to FFA, that is free fatty acid in feedstock, which makes it suitable for low grade oils and simultaneously catalyze esterification and transesterification process. But the demerit is that the reaction rate is 4000 times slower and low yield in comparison to the base catalyzed transesterification. Also, the catalyzed separation is difficult. There is a requirement of high oil alcohol molar ratio. There is corrosion problem, neutralization and wastewater treatment or high energy consumption are some of the other drawbacks of this process. This mechanism involves 3 steps: protonation of carbonyl group and results in carbon cation formation, nucleophilic attack of alcohol to produce tetrahedral intermediate, rearrangement of tetrahedral intermediate to release an alkyl ester and proton catalyst. So, a 2-step process, that is acid base catalyzed transesterification, has advantage over the single or the individual base catalyzed or acid catalyzed transesterification. For oils having high amount of free fatty acid, this 2-step process was recommended. First, acid catalyzed esterification followed by the base catalyzed esterification. It involves the 2 steps, that is first acid catalyzed was employed for esterification of free fatty acid to ester. When this free fatty acid level reaches less than 0.5 to 1% weight, then base catalyst was employed for transesterification step. The major drawback of this process is requirement of extra separation stages, washing and catalyst removal in both steps. The acid catalyst from the first step can be removed by base neutralization and in second, but it adds extra cost of base catalyst to the process. You can see in this equation the step 1 triglycerides with a acid in presence of acid. A triglyceride reacts with alcohol in presence of acid forming the diesel. So, in the first step the product is triglyceride plus RCOOR1 plus water, while in the second step this RCOOR1 reacts with the triglyceride in presence of alkali to form the monoalkyl ester. So, both this you will be getting the efficiency of the biodiesel production is improved, or the full utilization of FFA can be used. The next type is the heterogeneous catalyzed transesterification. The complex problems of homogeneous reaction were easily sorted out by using solid heterogeneous catalyst. Their characteristics like interconnected large pore system, high concentration of strong acid sites, hydrophobic surface, etc. helps in making this process feasible for industrial application. These catalysts include ion exchange resins, transition metal oxides and their derivatives, then some boron group based catalyst, alkaline earth metal oxide derivatives, carbon based catalyst, mixed metal oxides and derivatives, etc. So, this is the flow chart which shows the classification of transesterification catalyst. We have seen the homogeneous group and the heterogeneous group. Homogeneous you will have the acid catalyst and base catalyst, and the heterogeneous also you have the different types of catalysts. This is the flow chart of biodiesel production using the renewable resources. So, the oil extraction happens mainly by the expeller. If it is a seed, it is added to the expeller and oil is removed. This is used for the biodiesel production in the biodiesel reactor. Further, it is filtered. The product is undergoing this heterogeneous or homogeneous catalyst separation, followed by the washing, then drying, and the catalyst is reused. The ethanol is removed, the excess ethanol can remove from this, and you will see these biodiesel in the upper phase. So, it can be removed by the centrifugation and the glycerol is separated from it. Then this impure biodiesel can be distilled and vacuum distillation unit, and we will get the pure biodiesel. And the third type is the biochemical transesterification process, where the enzyme is catalyzing the transesterification. This application of enzymes eliminates downstream processing problems of chemical catalyst and has the potential to provide easy way to settle down problems related with the biodiesel production through the chemical process. Normally, the lipases are used in this biochemical transesterification, and the advantages of this biochemical transesterification process or the enzymes are, these are specific and selective towards substrates, it minimizes side reactions and impurities, then easy product separation and recovery, eliminates treatment cost of catalyst through recovery process, low reaction condition is required, these are biodegradable and environmentally acceptable, provide opportunity for catalyst reuse with great stability through immobilization technique. This table shows the advantages and disadvantages of different types of catalyst, which we have already discussed, which are used for the transesterification. The homogeneous acid catalyst, the advantages are esterification and transesterification occur simultaneously. These are insensitive to free fatty acid and water. It is a useful method if low grade oil is used, the less energy intensive, mild reaction conditions are required. But disadvantages, it lead to corrosion on reactor and pipelines, then very slow reaction rate, difficulty in separating the catalyst. In the case of homogeneous alkali catalyst, it is a very fast reaction rate, mild reaction conditions are required, less energy intensive. Catalysts like sodium hydroxide and potassium hydroxide are cheap and easily available, but the soap formation will reduce the biodiesel yield, increase viscosity of the product. The FFA is greater than 1% lead to soap formation. It is sensitive to free fatty acid content in oil, product purification problems, and produce huge amount of wastewater. Heterogeneous acid catalyst is insensitive to free fatty acid and water content of oil. Useful method of low grade oil, easy separation of catalyst. Here also the esterification and transesterification occur simultaneously. High possibility to reuse and regenerate the catalyst, but it has a complicated catalyst synthesis, lead to higher cost, high reaction temperature and oil alcohol ratio, long reaction time and energy intensive. The product contamination due to leaching of catalyst active sites is also a problem here. In the case of heterogeneous alkali catalyst, relatively faster reaction rate, mild reaction condition, less energy intensive, easy separation of catalyst, high possibility to reuse and regenerate the catalyst, highly reactive at high temperature and pressure. Soap formation will decrease the biodiesel yield and problem in product purification. Slow reaction rate, FFA Greater than 2% lead to soap formation, poisoning of catalyst when exposed to air, product contamination due to leaching of catalyst, active sites, energy intensive but quality of the product is good. In the case of enzyme catalyst transesterification, which is a preferred method for low grade oil, insensitive to free fatty acid content and water content of oil, the reaction occurs at low temperature and need only simple purification step. It is sensitive to alcohol, mainly methanol, because it is a biochemical reaction. Its effectiveness varies. Let us see what are the factors affecting the transesterification process for the biodiesel production. First one is the oil composition and free fatty acid content. Edible oils that contain less than 1% free fatty acid and no toxic components and are called high grade oils. So, the edible oils are known as high grade oils. It has only less than 1% free fatty acid. Recycled or waste oil and byproducts of the refining vegetable oil, some of the non-edible oils and animal fats contain higher levels of free fatty acids, and therefore, an esterification step is required using homogeneous acid catalyzed, supercritical enzymatic or heterogeneous catalyst process. This table shows the fatty acid profile of triglyceride feedstocks. You can see the different proportions of palmitic, palmitoleic, stearic, oleic, linoleic and linolenic acid. The second factor is reaction temperature. The rate of transesterification reaction is greatly influenced by temperature at which reaction proceeds. A higher reaction temperature can be instrumental in reducing the reaction time and decreases the viscosity. That is, it increases the reaction rate. If the reaction temperature surpass optimum temperature, saponification reaction of glyceride, triglyceride starts, which decrease the biodiesel product during homogeneous alkali catalyzed transesterification. It also influence on the reaction rate and yield of esters. Normally, the esterification occur at different temperatures depending on the oil used. The third factor is the alcohol to triglyceride molar ratio. The molar ratio of alcohol to triglyceride is very important factor for the effective yield of biodiesel. 3 moles of alcohol and 1 mole of triglyceride is required for the production of 3 moles of fatty acid, alkyl ester and 1 mole of glycerol as per the stoichiometric terms. The yield of biodiesel is enhanced if alcohol to triglyceride molar ratio is increased beyond 3:1 and it reaches a maximum. Further, increasing the alcohol amount beyond the optimal ratio will not increase the yield, but will increase the cost for alcohol recovery. The molar ratio is also associated with type of catalyst used and molar ratio of alcohol to triglyceride. In most of the experiments shown that it is 6:1. With the use of alkali catalyst, alcohol to triglyceride ratio as high as 21:1 is also suggested to some of the oils or fat. The reaction time. The rate of conversion of fatty acid ester increases with higher residence time. Initially, the reaction proceeds with a slow rate due to the mixing of dispersion of alcohol into the oil. After proper mixing and dispersion, reaction proceed at a higher rate. In general, reaction is completed within 90 minutes and biodiesel yield remain constant until the start of backward reaction. This backward reaction results in loss of ester as well as initiate the saponification reaction. The ester conversion rate increases with the reaction time. It will also influenced by type of reactor in which the biodiesel production happens and the water content and acid value of the triglycerides used. What are the advantages of biodiesel over the diesel? Petroleum diesel fuel is made up of hundreds of different hydrocarbon chains, that is roughly in the range of 14 to 18 carbons in length. It contains aromatic hydrocarbons like benzene, toluene, xylene, sulfur and crude oil residue contaminants. But biodiesel hydrocarbon chain are generally 16 to 20 carbons in length and contain oxygen at one end, which helps, that is around 11% oxygen, which enhances fuel combustion and therefore it contributes reduction in the exhaust emission and also the petroleum diesel fuel usage. So, it reduces the particulate matter, it reduces the sulfur dioxide emissions. These properties improve combustion efficiency and emission profile. You can see that the biodiesel fuel blend reduce particulate matter, hydrocarbon, carbon monoxide and sulfur dioxide emission. It can decompose easily under natural conditions and 90% biodiesel can be degraded in a week, in few weeks. Hence, it is a clean, renewable and domestically produced diesel fuel, which has many characteristics of a promising alternative energy source. It has negligible SOx emission as compared to petroleum diesel, with petroleum diesel which has sulfur content in the fuel and also has the high cetane values than the diesel fuel. What are the limitations of the biodiesel? The engine problems such as plugging of filters, caulking on injectors, more carbon deposits, excessive engine wear, oil ring sticking, engine knocking and thickening and gelling of lubricating oil are some of the problems related with the biodiesel usage. The detergent properties of FAME cause illusion of impurities and plugging in some parts of the fuel system. It also tends to form sludge and deposits, especially during long term storage. High content of FAME in diesel fuel leads to faster degradation of motor oil. Relatively high solubility of water in FAME cause large corrosion of metal parts. Besides, the other constraints in biodiesel production are high feedstock cost, shifting of food to fuel, technical constraints related with the pH, temperature, solvents and supports, catalysts, etc. in the transesterification process. So, in this module we have seen what is technically biodiesel, what are the properties of biodiesel, what are the feedstock used in the biodiesel, especially the edible oil, and how the non-edible oil crops are important over the edible oil crops for the biodiesel production. We have also seen that the algae is also capable of producing biodiesel, and also nowadays waste cooking oil or the waste oils are used for this biodiesel production in order to reduce the food versus fuel debate. We have also seen the process, the transesterification process involved in the biodiesel production. Here we have seen that the triglycerides reacts with alcohol in presence of catalyst to produce 3 moles of biodiesel and 1 mole of glycerol. And you have seen one oil requires 3 moles of ethanol. And we have seen the different types of transesterification based on catalyst used, either homogeneous or heterogeneous, acid or base catalyst. And also enzyme catalyst transesterification process is also there, where the lipase is used in the process. We have seen the different factors influencing the biodiesel production, like the oil composition, the FFA content, the molar alcohol to the triglyceride molar ratio, reaction temperature, reaction time, etc. We have seen how the biodiesel are considered as a clean renewable fuel over the diesel. And we have also seen the limitation of biodiesel like gum formation creating problem in the engine, then technical constraints related with the pH, temperature, etc. We have seen the cost of the feedstock is also reducing the commercialization of biodiesel production. Thank you.